Alrighty, welcome back to 353. Bright and early at 9 a.m. Isn't this fun? Whew. Alright, so let us start our next lecture about libraries. So we haven't defined what the heck is an operating system. So we said that the kernel is part of the operating system. It is the software that runs in kernel mode, again, kind of circular definition. But what else is part of the operating system? So, for instance, if you're an Apple fan, there's macOS, iOS, iPadOS, watchOS, tvOS. Are they all different operating systems? Or are they 99.9% the same? Well, it turns out they're all using the exact same kernel. They're all using, the same Darwin kernel, but they would all be technically considered different operating systems because typically what you care about for an operating system is what kind of programs or applications it could run, and you can argue all the different, a TV app is not the same as an iPhone app, is not the same as a Mac app. So technically, you could probably say they're all different operating systems, even though, 90% of the code is the same. So applications might pass through many layers of libraries. So what we talked about yesterday was, hey, the kernel lives in kernel space way down there. It does very important things like interacting with the hardware, but your applications typically do not actually use that system call interface. You probably rely on something like the C standard library to call it for you and use it for you. So if you have a very basic, is the C standard library, and you might consider the C standard library part of the operating system. If you have something more complicated, there's other libraries. There's like a system daemon library that abstracts hardware for your application. So you can tell, hey, this computer has different network cards, things like that. So like things like Network Manager might use that daemon to see, hey, what's an Ethernet device, what's a Wi-Fi device, things like that. LibreOffice, well, that probably use like a GUI toolkit. You can actually have a user interface. So that would probably use some GUI toolkit like JTK, something like that. And then that in itself would use a library to actually display the pixels to your screen, something like Wayland on most modern Linux systems. And then something like Firefox might use all of them, so you can mix and match libraries. So what is part of an operating system kind of depends on your application. So what it is, like I just said, depends on your application. Android and Debian, or whatever you're running your dev container on, they both use the Linux kernel, but the applications are different. Your Android application is going to be different than like the Hello World we did before. But Android and Debian both use the Linux kernel. So if I only cared about Hello World, you could actually transfer that Hello World executable to your phone, and if you're using an Android phone, and it would execute. In which case you might say that Debian and Android are the same operating system as if all you care about is console applications. So again, it's kind of weird. The answer is it depends. So as an aside, Linux distributions are usually considered to be GNU/Linux because Linux is the kernel, and GNU is basically like the standard C library and all the default applications you have, like LS, CP, things like that. So what the operating system actually consists of is the kernel and any libraries required for your application. So that is our definition of an operating system, where the answer is it depends. The only thing that is ironclad here is the kernel is definitely part of your operating system. Whether or not a library is, kind of depends on your application. So here is some review on compilation. So normal compilation in C, hopefully this is review for everyone. You have your .c file. You compile it either by hand or by using make or meson or CMake or something like that. And every C file turns into an object file that has all of the machine code in it and all the functions and everything like that. And then in a separate step, they're all linked together aka they're just kind of all mashed together to form a single executable. And now we can also know that these .o files are also just ELF files with code for the function. So this is review to everyone. Yes, any questions about this? All right, hopefully review. So there are two types of libraries, static and dynamic. Static libraries are included at link time. So say in some of those C files, you want to use them in different applications. Well, copying and pasting is really bad. If you want to make something reusable, you can compile it, create a library out of it, and then many applications can use your library. So static libraries are included at link time or compile time. So should know from before, there's a difference between compile time and runtime. So compile time, whenever I use GCC, it creates the executable, and then runtime whenever I try and execute my program. So if, let's say, my util foo and my bar files were something I wanted to reuse, I could, instead of linking them all in the executable, I can mash them all together, doing something called link them together as an archive, and then they're all mashed together in this lib.a file. And the idea behind this is that, well, instead of using this linking to the C files directly, your application can just link with this lib.a. But otherwise, this all happens at compile time. You get the same executable. It has the same things in it, and it gets linked together at compile time. So the only difference is that, hey, I have several things together, mashed together in lib.a here, and other programs can actually use it. So if I had like a main2, I could just link against lib.a instead of recompiling every single file again. So the other option is to have dynamic libraries for reusable code that gets determined at runtime. So the C standard library is a dynamic library. It's indicated on Linux as a .so file. Like other systems, it's basically the same thing. It's a collection of .o files containing all of the function definitions, but it's resolved at runtime. And idea behind this is similar to any other library. Multiple applications can use the same library. So pretty much everything you've ever written uses the C standard library, so your application 1 and application 2 can actually use the same standard C library, and the operating system can do some tricks with this. It can only load libc into memory once and share it between every single application, which is probably something you want to have a lower memory footprint. You don't want to load a separate libc for every single application that uses the exact same library, right? So even if libc was like 1 megabyte, if you had 100 programs using it and none of them shared, then you'd have 100 megabytes wasted for every single version of libc. So this is why it's a good idea to just do it dynamically. So how it works, same idea. We take all of our .o files, but instead of doing an archive, we do them under shared linkage, which adds some additional things to this .so file that helps the operating system find like where a function like printf is. And then now for our program, we don't have to, at compile time or link time, all we have to do is say, hey, what library we use. It will go ahead and kind of just double check it whenever we compile it, but it will create an executable that actually uses that library at runtime. So whenever you run your program, it then loads that function from the library whenever it is run. So now I can actually update this file, and I get run a different version every time it runs. Yeah?
So does it kind of act more like a database, and you only pull what you need dynamically, or?
Kind of like a database, but it's just like, yeah, you can kind of think of it like a database that just loads it whenever your program actually runs. So like when we did the strace on our Hello World program, we could see that, hey, it opened libc and it found printf and then it called that. So if we changed it and then ran the program again, it would find the new version of printf. But if we did it statically, then printf would be included in our executable and it would always run the same thing. And it wouldn't have to find anything. It would just be in the executable. It would just run printf. Drawback is there. If we update printf, we have to recompile our whole program again and everything like that, which we'll get into. So there's a useful command line utility for checking what dynamic libraries an executable uses. You can do LDD and then the executable, and that will show you all the dynamic libraries an executable uses, just in case you are curious. Might be useful for you later. We won't really touch in this course, just a nice aside. So why would we use static and dynamic libraries? So the other option, again, was to statically link our code. Again, static linking basically just copy-pastes all of the .o files directly into your executable. So if you change something in your library, in order to get the changes in your executable, you have to recompile it because it basically just copy and paste it into the executable. Some drawbacks compared to dynamic libraries: if you statically link, you're not reusing any libraries. Many common applications would have many duplicates. So for instance, if the standard C library was a static library, then if you use printf, you have a copy of printf in your executable. That's a copy of it whenever you compiled your program. And every single program running on your machine would have its own independent copy of printf, which is whatever it was whenever you compiled it, and that would be a lot of wasted space. And again, if you have to update printf, if there was a bug with it, hopefully there's not a bug in printf, but if there was, in order to get that new version of it, you need to completely recompile your executable. Well, if I use a dynamic library and I immediately get the changes, might there be an issue using a dynamic library? Has anyone ever written a buggy program before? Yeah?
What if the library you're using becomes deprecated?
Yeah, well, what about if it becomes deprecated, or even worse, what about if the new version now has a bug in it, right? If the new version now has a bug in it, you immediately, when you update that library and then run your program again, well, it now uses this buggy function, and then it blows up and it doesn't work anymore. But you didn't change your program at all, so now you get to go ahead and try and debug that with something that is absolutely not your fault. So really important that you write good software. So we'll see an example of that. So the big drawback here is dynamic libraries can actually break executables. So we talked about a ABI change, like what an ABI was before. There are certain things you write in C that suddenly change the ABI that we will go over today. Don't worry, you don't have to know this for the course, like what all the rules are. We'll just be exploring a little example that may or may not be slightly confusing. But let's just say we have a dynamic library that has a struct in it with multiple fields, and that corresponds to a certain ABI, like how that struct is laid out in memory. Whether you know it or not, there are certain rules for it. So the executable accesses fields of the struct. If an executable uses the fields of a struct used by a dynamic library, well, whenever you compile your program, it uses certain ABI. If you change it and the library compiles with a different version of the struct, and they don't agree anymore, really bad things will happen. So we'll have an example where the dynamic library just reorders the fields of a struct. So it just changes the order of them. That would not change the API. So say I have a point with an x and a y, and I define it as y, then x. And then later I'm like, I didn't like that order. I'll change it to x, then y. Well, that's the same API. Point has an x and a y. But the rules of C are that those have different layouts in memory. So if you never show the user a struct and you keep it contained in the library and the changes are only internal to the library, you will never have any disagreement between them. But if there is a disagreement, bad things will happen. So let's see what our example is. So C's rules for their ABI for structs, how they're laid out in memory. The fields are laid out in memory in the exact same order you declare them in. So C compilers all agree on this. They ensure the ABI of structs are consistent for a specific architecture. So if we had the following structs, if I had struct point with an X and a Y, and let's say this is my version 1 of the library. So in version 1 of the library, the X field is offset by 4 bytes. Everyone knows what an offset is, hopefully. So offset is just the number of bytes from the start of this file. So this struct here contains 2 ints. An int is 4 bytes. So the total size of the struct is 8 bytes. And well, if they're laid out in memory in the same order they're declared in, then if I give you the starting address of the struct at some arbitrary address, offset 0 would be the first byte of the struct, and that's where Y would be. So Y would start at byte 0, be byte 0, 1, 2, 3, because it's 4 bytes. And the X field would start at byte 4. So that's what we call offset 4. So for version 1, just looking at the X field, it's offset by 4 bytes from the beginning of the struct. And then in version 2, where we just flip the order of the fields, it now is offset by 0 bytes. So it's at the beginning now. So if we had a library that just dealt with points and we've made just this change, we will cause a whole slew of problems. So let's look at the code. So again, here, just to be clear how the struct is represented, after compilation, the translation is going to differ for each version. So for struct, for point v1 and for v2, it's basically represented as an array of 2 ints, if you want to think of it that way, because they're the same size and types. In version 1, where I had y first and then x, that's the same as y is like at the array at index 0 if it's an int array, and x is at array at index 1. And in version 2, x is at array at index 0, and y is at array of index 1. So is this clear to everyone? All right, so this is going to cause problems, and let me know if this hurts at all. So we're going to create a library called libpoint, and it's going to have these following 4 functions. So it's going to have a point create that takes an x and a y, and then it returns a pointer to a new struct. So internally, this would just malloc some space for that struct, initialize the fields based off the arguments, and then return you back a pointer to it. And then, well, this is C, so they're not methods, but we'll have basically a method to get the value of x given a pointer to the struct, and then how to get the value of y given a pointer to the struct. And then we'll have a point destroy, which is basically just going to call free. So here. So let's go into the example code. And again, stop me at any point if things get strange. So here is the library. So in point create, all I do is, also part of the library, typically you also have like a header file. So here's my header file that has the struct in it. So this is version 1, so it has a y and then an x. And then it has declarations for my 4 functions I'm going to define. So that's OK with everyone. That's my header file. And then in my point.c, this will be compiled to create my library called point. In point create, all I do is malloc, space for that struct. I get a pointer back, and then I just set the fields, and then return back that pointer I got from malloc. Get x, get y, they just access the field, and then destroy just frees it. So anyone have any problems with this? Perfectly cromulent, right? All right, so here is my example. So this would get compiled using this header file, which is version 1, which has y then x, into libpoint.so, which would be my shared library object. And then let's create a program that uses this library. So I would include this point.h, which right now, if I compile it with version 1 of the library, it would have y then x, which is the same order that the library was compiled with. And then here, I do a call to point create where x is 1, y is 2, and then I just print the points x and the y using the library calls. So the numbers I get are from calling x and y, but then you might be like, okay, well, as part of the library, I actually know the fields of the struct because it's defined in this .h file, so I can just get the points x and y coordinate just directly using the struct, right? I can just do p arrow x, p arrow y, right? That's okay with everyone? All right. So if I run this, where I compile it with version 1, so when I say compile version 1, that means of this header file. Oops. And all I'm doing is changing the order of the struct in this header file. So compile version 1 means I compiled this libpoint example with version 1 of this point.h file, and link v1 means I also compiled the library with version 1 of this header file. So if I run this program, what should I see printed? How tricky am I? Yeah.
1, 2, and then 1, 2 again.
1, 2, and then 1, 2 again, right? Yeah, see? Confidence. So 1, 2, 1, 2 again. Everything is all hunky-dory, right? So weird thing might be, because this is dynamic, right? This line is coming from calling my library functions, right? Which that's compiled separately than my executable. If I go ahead and I do make a version 2 of that library, so here I open version 2, the code is going to be exactly the same. I did not change any of the definitions of the code whatsoever. All I did is in point.h, I just swapped around x and y, right? So to simulate a update to the library and not an update to my program, I can run this under libpoint example, so compile with version 1. So this point example program was compiled with version 1 of my library, which had this as the header file it was compiled with. And then later, I came along, created version 2 of the library that changed the header file to flip the fields of the struct. I would have compiled this new version of my library with version 2 of that struct. So now this is using the fields in the, well, in memory, these fields are in the other order. I compiled this. This is now libpoint version 2. So to simulate that update, I can run it using this point example, compiled with version 1 of the library, and then linked with version 2 of the library. So if I do something like that, what's going to get printed? And this simulates a update. Yeah? 2, 1, and then 1, 2. So using the library, it's going to get 2, 1, and then 1, 2 as the next line. Yep. So close. So one of them got reversed. So why did that one get reversed and not the other one? It's a good question. Anyone know why that one got reversed? Yeah. So yeah.
Because struct is going to 0 for x, but at 0 there's a y. It's like the opposite.
So we have to look at who created the struct, right? So in this point example, so this point.h, if I'm compiled it with version 1 of the library, this point.h, that has y first, then x first, right? If I use point create, that's calling my library one. So that uses the order of like what the library expected it to be in too, right? So point create for the library, it was in version 2, it was x first, then y first. So with version 2, using the library, since this is one of the functions that's in the library, it went in memory. It went x first, then y first. So if I use this point get x, well, get x also uses the library. The library is going to agree with itself, right? So it thinks that x came first, so it will get x. And then using point get y, well, it knows that it was x and then y, so it will return the y. But if I just use the struct directly, right, this is my program that was compiled. It uses, it accesses the fields of the struct directly, and they get baked into my executable whenever I compile it. So this p.x, if I compile it with version 1, that will think x comes second, and then y comes first. So that's why if I do this, well, this is just going to access the second element. This is always going to access the first element. So in this case, it's going to be the reverse of what I think it should be, right? The library agrees with itself, but this does not agree with what I compiled the library with. Isn't that fun? Yeah.
But like in version 1, we put y before x, right? So why was it like 1 and 2 instead of 2?
Sorry?
Like in version 1,
Yep.
we put y before x, right?
Yeah.
Like the alpha shows like 1 and 2 instead of like 2 and 1. Right?
Yeah, so this one using the library shows 1 then 2, right? Because it agrees with itself, right? So the library actually created the struct. If we compile the struct with version 2 of the library, it goes x and y, right? And then this get x, it knows if it's compiled with version 2, it will access x at the first slot at index 0, right? So this would return 1, this would return 2. Using the struct, if we compile this with version 1 of the library where y came first and then x came first, this is going to correspond to the second slot, right? And this y will correspond to the first slot, which disagrees with the library. Everyone kind of see how it's a really subtle thing, but shouldn't break things, but they've actually broken code for literally every single program on the planet. C++, the standard C++ library, did a change like this, where they reordered fields, I think, of a list, and then every single program that used a list was now wrong and didn't work. So they had to recompile literally every single program on the planet. That was fun. Yeah, was a good question?
More just like a clarification. So it is, I mean, the takeaway, I guess, kind of is if the library gives you functions to do stuff, don't take shortcuts.
Yeah, well, takeaway is if you are the person writing the library. So if I am the person writing the library, let's go up here. If I'm the person writing the library and I define a struct, I can now no longer change it if it's included as my header file, and then you can compile it into your program, right? Because if I didn't do this, if I just said, struct point and then didn't give a definition at all, and then completely hid it from you, and then you can only access it using the library, then I can willy-nilly update the library. The library is always going to agree with itself, right? But if I define a struct and then you use it, I'm now no longer allowed to change the struct whatsoever. Otherwise, I will break every single program on the planet that uses your library.
So in that case, the definition would go in the definition file.
Yeah, in that case, if I wanted to do it properly where I want to be free to change the struct, I don't define it in the header file. I only define it in the C file, because then only the library is going to know about it, which is fine. You can change it willy-nilly. And then I can also simulate other weird things. So if I compile with version 2, oops. If I compile with version 2 and link with version 2, then they're both going to agree with each other. It's fine. but that would mean like, hey, I had to recompile my program, which kind of defeats the purposes of a dynamic library. Or I could also be like, hey, I updated my library, it's now version 2, but you're using an old system that only has version 1 of the library, in which case it's going to disagree the other way. Doesn't matter, it's going to flip them around. You could imagine also if this was a game or something like that, you update a library and then your whole game flips diagonally. That would probably be kind of weird. So yeah, probably don't want to break things using that. All right, that okay-ish with everyone? You don't have to really care about the details. The really important thing is that, hey, some things actually correspond to an ABI. You can't break an ABI if you're using a static library, or if you're using a dynamic library. If you're using a dynamic library, you have to be very, very careful about your updates. Otherwise, you will break every single program on the planet, and it will be bad. So how I did that is a little bit of magic. If you want to simulate library updates too, there's this environment variable called LD library path, and that will actually tell the C runtime, whenever I start running this program, look in this directory for the library first. So I could set LD library path to build v1 or v2 to simulate a library update. So you can do this to simulate a library update yourself. So even if you ran the one with compile version 1 and link with version 1, that's just at compile time. If I want to simulate a library update, I can set LD library path to search for version 2 first, and then it doesn't matter. Even if I use this program where I originally linked it with v2, well, LD library path is going to search for the library in this v2 thing, or v2 directory. If it finds it there first, it will immediately use that one. So it will disagree with itself and have the same problem we had before, which is not great. All right, so there's more just in case you need to see that. We can go on to the next topic since I think I hopefully explained it a bit clearer. So the too long didn't read problem is like mismatched versions of the library causes problems, right? Our original thing had a struct point. In both versions of the library, all I did was change the order of the fields. Has the same API. Struct has an X and a Y, but I suddenly changed the ABI even though I didn't even realize it. So the too long didn't read is if you expose a struct, it becomes part of your ABI, and now you are no longer allowed to change it. So you can try any of the combinations. If you wanted to change it, like I said before, proper stable ABI would be to hide that struct from point.h and only use it in your point.c file when you compile your library. So there's a scheme called semantic versioning that's supposed to help developers know whether or not a library update will break something or not. You can see it at semver.org. Basically, it's a set of rules to actually version our software. So a version number should be like all numbers. It should be number.number.number, where the numbers are major.minor.patch. And the rules are we only increment this major version if you make a version with an incompatible API or ABI change. So if you see this major version changes from 1 to 2, that means for sure I need to recompile my program. And if I want to not recompile my program, as long as the major version is the same, it should work even if you upgrade that library. The other one is this minor version. So you should increment that minor version if you add functionality in some backwards compatible manner. So like I add a new function in version, 1.1. Then I know, hey, my program needs at least version 1.1 because I need this feature. Should also work with 1.2, 1.3, 1.4, so on and so forth. And then if I don't add any new functionality and I just make a bug fix or something like that, the rule is I should just increment this patch version so it goes up from 1.11 to 1.12 or something like that. So that's generally the rules for doing dynamic libraries, because if you're using a dynamic library, you need to make sure you write it following these rules. Otherwise, you're going to cause the user using your library, if you break things for them, they're going to get really mad at you and then probably no longer use your library and probably send you a nasty email or yell at you or, I don't know, troll you on something. So, other fun things we can do is, well, the C standard library is a dynamic library. Believe it or not, it allows you to debug easier. So we can control it using the environment variables. Last example I showed you with LD library path. You can also do something called LD preload, and that forces a library to get loaded before anything else runs. So for example, let's consider this silly program, and this is always fun. Don't save. So let's consider this fun program. So this program, int main, int malloc, size of int. Everyone, what's the size of an int? 4. So this should return a pointer to 4 bytes, right? All right, so I cast it because it's C to a pointer to an int. And then I print off the address I got back from malloc, right? And then I free it. No memory leaks, no nothing, right? OK, so fun thing I can do is, let's say I wanted, everyone's used Valgrind before, right? To kind of check if we have any memory leaks or anything like that. So I could write my own kind of memory checker if I want. I can define my own malloc and free. And what I'm going to do is define my own malloc and free, and I'll just have it print out whenever malloc and free happens, so I can just kind of debug what's happening, make sure everything lines up. So I created something called LD preload. So I called it liballoc wrapper that wraps malloc and free, so I can see what things are doing. So if I just ran this program normally, I just get x equals some pointer value, right? So if I run it with this, I can see all of the calls to malloc. So call to malloc 4. So that's the size of an int, right? I got back this address. So this is what malloc returned. And then here I do x equals. So this is from my program. This matches the call to malloc, right? And then I call free of that same address. What the hell is this? Anyone, any guesses? Yeah.
Is that a heap header?
Heap header?
Something like part of the original malloc that you had to like?
Nope.
No.
No, so this happened after. So this is all in order. So malloc 4 happened first. Yeah.
Is that where the string is?
Is that where the string is? Very warm, I would almost count it. Yeah.
That's for the
Terminal,
terminal.
no. That one was warmer. Anyone else with a more, using that idea but more nitpicky? Yeah. The print the terminal? Close. It's basically, that memory is being used by printf itself. So that's where this is stored in memory, right? Because it has to, printf, it needs to use some memory. So it needs to format my string, right? It needs to take this percent, like this is a string with a %p in it. It needs to take this string and replace the value I give it, like replace the %p with the value I give it, right? So it needs some memory in order to do that. And turns out that, well, printf needs some memory, and this malloc call is from printf. And do they ever free it? No, they don't ever free it. Well, let's see what, if I run Valgrind on this alloc example. Let's see what this says. So it says 2 allocs, 2 frees. 1,028 bytes allocated. Well, that agrees with what I had before. I saw 2 malloc calls, 4 and 1,024, so that's 1,028. But I saw 1 free. They didn't ever free that. This never got freed, right? But for Valgrind, it says it was free. Have you guys been lied to this whole time by Valgrind? Any guesses as to what the hell is going on here? Yeah.
Yeah, maybe when you call printf, it automatically allocates, and then when you when you return, it automatically releases.
When you return from printf, it automatically releases?
I don't know, maybe that's from the library.
Yeah.
Does printf have a free function inside?
Printf has a free function inside? Nope, just uses malloc. So if it was to free it, it'd have to call free. Yeah.
Does it get freed, like, kind of after the program terminates?
Does it get freed after the program terminates? Ish, yeah.
Does it free in the one malloc call?
In the what?
Like, do both get freed in the same malloc call?
No, they do not both get freed in that one free call. Only my 5 or my 4 byte one does. So, turns out there is a rule here. So if you look at the documentation for Valgrind, it actually cheats a little bit. It has this little blurb here that says, the GNU standard C library, libc.so, which is used by all programs, may allocate memory for its own uses, aka what we saw in printf. Usually, it does not bother to free that memory when the program ends. There would be no point since the Linux kernel reclaims all processes resource when the process exits anyways, so it would just slow things down. So we've been telling you to free your memory all the time, and the standard C library doesn't free their memory. That seems unfair, doesn't it? So the reason why they can get away with this is because if I had a more complicated program, that 1,024 bytes, that gets reused for every single printf call. So it only mallocs the first time you call printf, and then internally it reuses that memory every single time you call printf over and over and over again. And, well, it wouldn't actually know when to free it because the only safe time to free the memory that printf uses is after the last call to printf. And if you're writing the C standard library, there's no way to tell what the program's last call to printf is. So you simply just do not free it. And when your process terminates, the kernel's going to reclaim all the memory associated with that process anyways, so there's no point to free it because, well, you don't know when that memory is going to be last used, right? If they were wrong and they just freed it whenever they thought what the last time you called printf is, and then you used it again, then that would be a use after free, and that would be really bad. So you can make this argument if you are writing a library, but unfortunately, it does not excuse you from not calling free. So you are not writing libraries for the most part. You will a little bit in this course, but for the most part, you're not writing libraries, you're writing executables. Your executable should still call free. You only get this get out of jail call. You only get to do this if you're writing a library. Yeah?
Does Valgrind treat it as if it's been free? Because in the terminal and Pro 2 calls 2 free.
Yeah, so Valgrind actually, like special cases, any allocations that come from Libc, and it counts it as freed, so, because there's nothing you can do about it, right? If it doesn't free its own memory, it's not like you're gonna free its memory for it. So there's actually, like hard-coded in Valgrind, it will just mark anything from Libc as freed, so it doesn't bother you. Yeah?
Does it apply to like all the functions that's like in like printer and file libraries?
So,
Not just printf?
no, this only applies to Libc.
Oh, okay.
Well, if you defined your own printf or own version of it and you used memory, you could make that excuse too, but if you use Valgrind on it, they're not going to special case that, and it's going to look like memory's not freed and there's a memory leak. But you know that, oh, you know, I can use the same excuse as the standard C library. This is actually okay. But So you have to argue, if you leak memory in Valgrind, you have to argue that you are correct. Yeah.
What if we did the same kind of thing that we just did with malloc and we made our own printf?
Yeah, if you made your own printf that malloced, it would say you leak memory.
So how does it know that you're using the libc version?
So how does it know? So without getting into too many details, it basically just instruments everything. It knows that you loaded the libc's version of printf, and it knows basically any malloc that comes from printf, it's just going, or any malloc that comes from libc, it's going to just assume it's freed. Yeah.
So just to follow up, then, should we manually free it, or should we like?
No, you just ignore it. If Valgrind says it's okay, it's okay.
Okay, no, like for if we define our own function and it shows that there's a memory leak.
So if you define your own function in a library and there's a good reason for you not to free it, then you can argue that that leak's okay, because Valgrind will say there's a leak.
Okay.
But you have to argue that it's okay. And if you're using Valgrind, there's a certain way to mark things as like, hey, don't report this as a leak. It's fine. But there's certain ways you can do it in Valgrind to be like nice. But yeah, basically, you'd have to argue about it and then tell Valgrind that, hey, no, this is totally okay. I know what I'm doing. Trust me. All right. Other cool things you can do is you can detect memory leaks with something like address sanitizer. So there's some sanitizer tools built into Clang, now GCC. You have to recompile. So we use Meson for this course to build everything because it makes it easy. If you want to detect memory leaks using this instead of Valgrind, you can recompile your program, set it up with this option, desanitize address, and that will basically compile all of the malloc and free checks directly into your executable, and it'll run a bit faster than Valgrind. So you can try this if you want. We won't see an example of it, but that's something you can try. Also, so you might notice that system calls are really rare in C. Generally, you use things from the C standard library instead. So most system calls do have like a one-to-one correspondence with the C function, but they do other things. So system calls don't set error no or anything like that. So the C version set this global variable called error no. They might also buffer reads and writes to reduce the number of system calls. So printf might not actually trigger a write in some cases. It usually only triggers a write if there's a new line. Might try and simplify interfaces like a function that combines two system calls together or add some type of new feature. So for instance, C has exit. If I do system call exit, that means program's done, process is done running, it exits immediately. No pass and go, no collecting $200. But C has its own exit function. So the system call exit, again, immediately stops. The C exit, they added a feature to register functions that get called before the system call exit actually happens. So if I have a program like this, so I have this fini function that just prints a string called doFini, and then I have a main that calls this @exit function. What @exit does is register a function to run whenever I actually call exit. Then I do a put s that basically just prints do main, and then I return 0 from main. So returning a number from main implicitly calls exit from the C standard library. So this return 0 will call main, and because it doesn't immediately do the system call main, it does the C exit. It will check for any registered functions and run them before my program actually exits, in which case it should print doFini, even though I don't call it from here. So if I run this, it's called @exit example, I see that I see do main, and then return, which calls exit. So it's the exact same thing as if I just did this. They mean the exact same thing. And then compile, oops. So they mean the exact same thing. So if I run that, I get do main, doFini. But if I did the system call one, like if I did system call exit right after do main, process would be done, I wouldn't see that do fini line because, well, this is the C version of exit that adds some additional features. Neat, huh? So let's quickly wrap it up in the 1 minute we have. So operating system provided foundation for libraries. We learned about dynamic libraries, comparing them to static libraries. A little bit how to manipulate the dynamic loader. You absolutely do not need to know that for this course. That's for like if you want to exploit things or just play around with stuff. And we saw example usages of like just changing the ABI that broke things without any API changes. Again, just know the high-level rules. You don't have to know the details. So just remember,